All right, welcome back everybody. This is video 2 on section 8.11 of AP Calculus, volume with the Washer method, with respect to the X and Y axis. So we're going to go ahead and do a couple more examples here. Let's look at example 2. We're going to find the volume of the solid generated by revolving the region bounded by x equals sine of y plus 4. And x equals negative y squared plus 7. Make sure you note that the plus 4 here is not inside the sine function. That's a common mistake that I've seen students make. Make sure, if I wanted that plus 4 to be inside the sine function, there would be parentheses here. There aren't. So, anyway. Here we go. A rough sketch of what this looks like. X equals negative y squared plus 7 is a parabola that opens to the left, like so. And x equals sine of y plus 4 is a sine curve. I'm not sure exactly where the curve is going to hit this, where exactly it's going to hit the parabola. So, this is a rough sketch. But what I can tell from this sketch, in helping me get set up, is number one, since we're going around the y-axis, number one, I can tell that this is a washer-based solid. Number two, I can tell that the outer radius is the parabola, since that's further away from the axis of rotation, and the inner radius is the sine curve. So that gets me a lot of information as far as setting this up. I'm going to have the pi times the integral of the outer radius squared, so parabola squared, minus sine curve squared. Now, all I need in order to answer this question is I need the y coordinates of these 2 points. So I've got to solve this set of equations. Probably the easiest, I can set these equal to one another and try and solve that by hand, which is disgustingly ugly. I can try and use my calculator to solve it, which is a little better. But in fact, what I'm going to do, I'm going to go ahead and graph the inverse of each of these functions on my graphing calculator. You remember we used this little trick when we were finding areas between curves. If you happen to catch that video, we can graph the inverse, and the area of the region is the same as the area of the region formed by the inverses. Similarly, we can do this, and the region that I'm about to graph on my calculator, the volume of that when I go around the x-axis is the same as the volume of this region when I go around the y-axis. So it's just a little mirror image. But what happens here when I make this graph, this confirms for me that the parabola is the outer curve, because this volume is just like if I was revolving this inverse region around the x-axis. The parabola is the outer curve, the sine curve is the inner curve, and these intersection points are the same intersection points as these intersection points, except that the coordinates are reversed. Okay, so when I find the intersection points on this curve, the intersection points will be the opposite, or the inverse. The coordinates will be flipped from the intersection points on our original. So let's go ahead and we will find these intersection points. First we'll find this intersection point right here, which is the lower of the two intersection points. And this is this point, negative 1.97932, 3.0822918. Well, on this picture of the inverse, those coordinates would be flipped. So this would be 3.082, comma, negative 1.979. And so we want the y coordinate of this point as our lower limit of integration, since we're integrating with respect to y. So I'm going to go ahead and, let's see, negative 1.97932 is going to be my lower limit of integration. And my other intersection point give it some time to calculate here. There we go. And this intersection point right here is going to be the same except with coordinates flipped. So that's going to be 4.988 comma 1.418, and we want the y-coordinate of this intersection point. So when we graph the inverses, in real life, I want the y-coordinates of these intersection points. Those are the x-coordinates of the inverse when I graph the inverse on my calculator. So that's going to be 1.41831, 0.4183101. Okay, now I've got it all set up, and I can go ahead and integrate this to find the volume of this solid. So I've got pi times the integral of the quantity negative y squared plus 7, quantity squared, minus the quantity sine of y plus 4, quantity squared, with respect to y, from negative 1.97932 to 1.4183101. Oops. And I want to close parentheses. There we go. And let my calculator find the volume here, which is going to be 227.549. All right, one more example. We're going to find the volume of the solid generated by revolving the region bounded by y equals x squared plus 2, y equals negative x plus 4, and y equals 6 around the x-axis. So we want everything in terms of x. We've got all these equations in terms of x, so that works nicely for us. First, I want to punch them into my calculator. I'm going to scroll here a little bit so that I can see them to type them in, and I don't have to be toggling back and forth between my calculator and my sheet of paper here. So we've got y equals x squared plus 2. I know what that looks like. We've got y equals negative x plus 4. I probably didn't really need my calculator to graph this. And we've got y equals 6. And there's what my graph looks like. And the region we're talking about here, let me sketch this by hand. The region we're talking about here, y equals x squared plus 2, y equals negative x plus 4, and y equals 6. We're talking about this region right here that's bounded by all three of those curves. And so now what happens here is we have a transition of boundary. We talked about this when we were finding area, but along the bottom here, this line is the lower boundary, the inner curve, the inner radius. And then right here at this line, the lower boundary changes, and it's now this parabola instead. So we're going to need two separate integrals in order to find the volume of this solid. Both of them, of course, are going to be washer-based solids since we're revolving around the x-axis. So we're using this as a washer-based, going to form a washer-based solid. This is going to form a washer-based solid. So I'm going to integrate this piece first, or find the volume of this piece first. Okay, so the outer radius here for this one is 6. It's going to be 6 squared, and the inner radius is the line negative x plus 4. And that starts at this point right here and ends at this point right here, whatever they are. I'll worry about finding those in a second. And then I'm going to add to that this other volume, which, color that in pink. This region right here, where the upper curve is still 6, but the lower curve transitions to be the parabola. And now all I need is my limits of integration, which are going to be the x-coordinates of these pertinent points on the graph. So let's find those pertinent points on the graph. First intersection I want is between these two lines. First curve, second curve. I think all three of them intersect at the same point. That's what it looks like. I'm not 100% sure, but that's at the point -2, 6. So I want the x-coordinate of that as my limit of integration. And then I've got the next intersection point over, which is between the parabola and the line y equals -x plus 4. That's at the point 1, 3. Wow, those were nice limits of integration. So that's going to be the upper limit of integration for my first integral and the lower limit of integration for my second integral. And then I need one more intersection point. I think this is probably going to be at x equals 2, based off of what I've seen so far in this particular problem. Wouldn't it be crazy if it was like 2.1? Nope, it is 2. Then we have all our integrals. I could go ahead and try and integrate all this by hand, but I'm going to go ahead and use my calculator to find the value of this integral. So let's go out to our main screen, and we've got pi times the integral of 6 squared, I'm just going to type 36, minus the quantity -x plus 4 quantity squared with respect to x from -2 to 1, plus pi times the integral of 36 minus the quantity x squared plus 2 quantity squared with respect to x from 1 to 2. And this should lead me to my answer. I get 193.103. Let me verify that I typed everything in correctly. There that is. Yep, it all looks good. And so my volume is going to be 193 I forget what the decimal digits are, 103. And there's my volume of that solid. So sometimes when we're finding volumes of solids, we even need to break it down into two different solids if we have a transition in our boundary, which is something we saw in area, and it's something now that we see with volume as well. All right, that takes us to the end of this video. We'll come back next time for lesson section 8.12, where we're going to talk more about volume with Washer method and look at a bunch of examples. And wow, then for those of you who are in AB, we'll be finished with the course. That's astonishing. All right, anyway, have a great rest of your day, everybody. We'll see you next time, and enjoy yourself. Bye-bye.